Okay, so I'm building. I've built a custom controller for the robot, and it was based on the robot operating system. And why a custom controller? Because I can, mostly, if I'm honest. And some of the specifications I had is because of the arms, I wanted to make sure I could actually control them both independently, and I wanted free-axis joysticks. So I ended up building this, and it's a custom controller, similar to the one that James Bruton has developed for his thing, but this has a full-blown Raspberry Pi with the touchscreen display built in, a pair of free-axis joysticks, and a bunch of incredibly satisfying chunky buttons. Mostly, I did that because I love cranes. I'm not going to lie. So the big remote controls that they have, the industrial things, I just love the look of them, the ones that are slung around people's necks, and I wanted in on that action. So the requirements were that I wanted the free-axis joysticks, lots of switches for switching mode. One of the switches, for example, this one here, when it's toggled up, this will control the drive of the robot, and this controls moving the head around. The idea is if you're moving around and driving, I can actually see the display from the eyes at the same time. And when I switch that down, it switches so I'm controlling the arms instead. And yeah, so the video feed will also show telemetry. So I've already got the battery broadcast across ROS, and that can come up on screen. So yeah, just showing you the thing. So the robot operating system. It's not actually an operating system. It put me off for a long time because I assumed that I'd have to learn how to do something completely new on a different platform and all the rest of it. And it's not actually an OS, so that made it a bit simpler. It's open source, BSD licensed, and it actually runs cross-platform. So you can run it Windows, Linux, and even on Arduino, which is incredibly handy, as I'll come to in a minute. Supported by pretty much every language. And it was created in 2007, so it's been around for a while, and there's loads of libraries for it. And basically, the robot operating system is a bunch of pipes. So you've got it's built around a subscriber-publisher model. So the idea is that if you have something like a sensor, it can broadcast, it can publish to one of these channels, and anything that is interested in those tasks, that information, can listen, and multiple nodes can listen at the same time. So for example, on the robot, I could have a node that monitors the battery to say, okay, if it gets below this level, do something. But that data can be broadcast once and used by multiple endpoints, so I can also see it on the controller. The nodes I just mentioned are basically a self-contained script or executable, and they typically do a job. So I have one for the motor control, the motor driving, one for the head driving. I have one for sending control signals for the motor, and one for sending control signals from the for the head, and so on and so forth. And those last two actually run on a Teensy. So there's something called ROS Arduino, and there's packages for various other microcontrollers as well. But the idea is you can run ROS nodes directly on the Arduino, such that it spits data across via serial to, in this case, the Raspberry Pi here, and it handles the communications to the master node, which is in the head of the robot. And the handy thing here is that it means I can have multiple controllers for one robot. So as well as having the controller, I could actually have a workstation version running on a PC, for example. Or if I wanted to have one person driving and another person controlling the arms, we can have that split concern by building another controller. Messages are sent to topics. So you have the node, which is the head control node, for example, and the head driver, and this publishes to a topic called head control. Anything interested can listen into that, regardless of the topic. Now, the standard messages typically contain floats, ints, strings, and arrays thereof. If you want custom messages, you can. You just have, there's a library definition that you can create, a message definition you could create in the robot operating system, and So if you want a custom struct in there, you can do that. I just went simple. I had an array of floats flying around. So when you move the joystick around, it's the teensy translates that into mixed values to send directly, essentially straight through to the breadboard. So rather than sending the joystick signals, which is what I was doing to start with, and that introduced lots of lag at each point when it wanted to be processed, because of the speed of the teensy, it was just doing that job very quickly. It could mix the values and send it straight through. So all it had to do was send it through straight to the robot, and it did it. And that's reduced lag to not be noticeable. Even when I was at the end of the garden controlling it right at the limit of the access point, it was perfectly fine. Right, so I've got a really nice diagram here that nobody can see. So the way it works is you have in this case anyway, you've got the teensy, which sits under here, which connects through to the Raspberry Pi. It connects to an access point over Wi-Fi, the same access point as robot, as MacFeegle Prime. The Raspberry Pi in his head, I still love that feature. The Stereo Pi is acting as the master node, so everything you want to talk to all goes via this node. That Raspberry Pi then has a motor node, a head node, and a battery node. The battery node just monitors the battery levels via the breadboard. The motor node does what it says on the tin. It uses the breadboard library, connects through to the motors, and the head control simply controls these two servos here to move the head around. Once I go a step further and actually get the teensy working in here for the arm control, that'll be another node, and again that'll likely be running on the teensy directly just to reduce the amount of time. So gotchas. Problems I had. For one thing, I mentioned the parsing, where you had problems. Basically, just because I was getting things started, I was using strings everywhere and doing CSV parsing, and I can hear all of the devs and coders going, "Oh, why are you doing that?" Because I didn't know better. So once I found out how terrible that was, it was basically causing enough lag that I'd move the joystick, and a few seconds later the robot would move. Yeah, you make it work. You make it work better, and then you make it work fast. And I went through those iterations. So yeah, after I switched to strings of floats coming directly from the teensy, I've managed to get the control signals going out at around 30 hertz. And that's fast enough for the speed of the robot. It's perfectly reasonable to control it. For the battery data, I actually specify 1 hertz. 1 hertz? Someone will correct me. And that's because the battery isn't going to change that fast. So you can specify the rate at which messages are sent so that you don't swamp the various nodes on the system. And so next steps, add more sensors. So you may have seen there's lots of gaps around the edge, and he's missing his bumpers on the front. There's a design for a bunch of time of flight sensors on there. I just didn't have time to print them out. So I've been a good boy, and I've been using my 3D printer flat out to do visors where possible. So that's been kind of running full whack and minimized some of the work I can do. But the great thing with the use of ROS is that these sensors, as Mark and Rob mentioned in Teradyne, they will be handled by the microcontroller, and then they'll just be fired as packets, messages into various topics around our ROS. There'll be the line following and cliff sensors, so if it approaches an edge, it won't fall off, similar to a Roomba. And the Stereo Pi will be brought to bear. So I've got the dual cameras up here, and they're actually ROS libraries that allow you to take stereo feeds from a camera and then convert them into depth maps in real time. I've never done any of that before, so I'm completely learning as I go, which is part of the fun, really. And for arm control, there are various kinematics libraries because the maths is beyond me, I'll freely admit. But again, it's open source, the libraries are out there, and I can just use them. So I need to figure that out. But there's the MoveIt kinematics library, which seems to be the one that's most developed. And you can basically give it a model of the robot in its entirety, the size of the the various arms, and it'll even create a collision avoidance mesh so that it won't try and ram itself through its chest. That means I'll be able to control the arms a lot easier, because doing it manually, as you saw in the video with the things, or even just using the joysticks would be a nightmare. That's it. I'm at the Q&A part now, my slides, so I've no idea how long I've taken, but yeah, if anyone has any questions.